In Section 2, we are looking at soil pressure behavior for an isolated footing. We will focus on how load eccentricity changes the soil reaction. We keep our footing geometry simple, so we can see the uniform, trapezoidal, triangular, and partial contact pressure distributions clearly. To compute the average pressure, we simply divide the applied load by the plan area of the footing. This gives us Q equals P over A. The area is B times L, so any change in load position changes the distribution while keeping the average fixed. Case 1 is centric loading with zero eccentricity. The load sits right in the middle, so the entire base shares the same soil pressure. The pressure is uniform and equal to P over A everywhere under the footing. Case 2 is a small eccentricity that stays inside the kern. The pressure becomes trapezoidal, with one edge carrying a little more load than the other. Our formula for the extremes is Q maximum or minimum equals P over times 1 plus or minus 6 E over L. Case 3 is the limit where eccentricity equals 1/6 of the length. At that moment, one edge of the footing reaches zero pressure, leaving a triangular distribution that peaks at 2 times P over A. The minimum pressure is 0, and the maximum is 2P over A. Case 4 is large eccentricity outside the kern. A portion of the footing lifts off, so only part of the base carries compression. In that case, the pressure spikes near the loaded edge and follows Q maximum equals 2P divided by 3B times the quantity L over 2 minus E. These 4 pressure distributions show how we must check the kern and avoid liftoff. When the load stays centered, the pressure is uniform. As eccentricity increases, one edge sees more pressure and the other can lose contact, which is why we always compute both Q maximum and Q minimum.